Hello everyone. In this video, we are going to look at free vibrations of Single-DOF systems again, but this time with viscous damping. So you have something in the system that basically dissipates the mechanical energy, and the force of it or the torque of it is proportional to the velocity in the system. So if it's a mass spring damper system, this linear viscous damper, the force of it is basically C times x dot, and it's in the negative direction of motion. So in this case, that you have this mass spring damper system and no external force, again, because it's free vibrations. If you draw the free body diagram of the object, again, you have mg and you have n, which will not affect the x motion. And then if x is to the right, then the force of the spring and the damper for spring is k times x, where x is measured from the static equilibrium position, and the force of damper is c times x dot, or c times velocity. So this damper is something similar to shock absorbers that you have in your suspension system in your car, okay? Their forces is almost linear, and that is when you have an object that is submerged or merged entirely into a fluid. So that is coming from the shear forces and the drag forces from that fluid, okay? So as long as it's moving relatively slow, sometimes it could be a little bit fast too, but mostly it is for a viscous material, okay? So for air, it's not really a big thing. For air, the drag force is really proportional to velocity squared. But for viscous material like lubricants and oils and something, that is mostly a linear force. So going back here, the equations of motion, as I said, is ma or mx double dot equals negative cx dot negative kx. Bring those two terms to the right-hand side, and you get this second order ODE, again linear with constant coefficients. If you find the characteristic equation, that is this quadratic one, but this time the roots can have complex roots, or you can have non-complex roots depending on these values of c over m and k over m. So if you find the roots and you write them as a complex number, they are going to be negative c over 2m. That's the real part of your roots. And then plus minus I times this square root is going to be the imaginary part of your roots. Again, if this number is negative, that means your roots will not have a complex root. They have real roots. So it depends on whether under this square root is positive, negative, or zero. So now we can do some simple modifications here and basically write this denominator like this, where you see that those two square root k's cancel, the two square root m's multiplied, you get the m. And here you can factor out a k over m under a square root from this. You get this one. And now you are going to call this ratio here, this c over 2km, and because this k over m, this guy is the natural frequency of the system from my previous lecture. This is the natural frequency of the system when there is no damping, correct? If the c was 0, the natural frequency of the spring mass system is square root k over m. And this is 1 over that, basically, you see here. So this new guy, c over 2km, which accounts for the damping coefficient, c, this guy, we give it a new name, that c over 2 square root km is this entity we call damping factor. Okay, we learned that this omega n, the unit for it is radians per second. But what about this zeta here? This zeta, or this damping factor, what kind of unit does this guy have, right? So if you look at this, the unit for c is what? It is force divided by speed. So it's Newton over meter per second, or it's Newton second per meter. That's the unit for c. So if I go and look at the units of this zeta, it is Newton second per meter divided by 2 times square root of k is Newton per meter, and m is kilogram. Okay, so what would you get? Now kilogram, if you want, because it's mass, you can write it as F over A basically, and F is Newton and A is meter per second squared, so you can write it as Newton second squared per meter. That's another way to write it. So if I do that, this is Newton second per meter, and this is 2 square root of Newton times Newton second squared over meter, and there is another meter here, so it's going to be meter squared. And of course, if you bring this one out, that's going to be Newton second meter, that's Newton second meter. So you see this zeta has no units. Okay, so it's a unitless entity. It has no units. It's just a ratio with no units. That's why we define it the way we define it. Okay, so it is just a constant, and the value of it will determine, as we'll see, the behavior of the system. So if that's the case, then looking at what I have over here, since this square root m over k is in the denominator, I can bring it to the numerator and I can write this as negative. This part of it is zeta, and this I can bring it to numerator and write it as square root k over m, so that part is going to be omega n. So you see the real part of your roots is simply what? Zeta omega n. And if you look at the imaginary part of it, this part, this is omega n, and this is 1 minus zeta squared. So that's what you can write here. So the roots of your characteristic equation are negative zeta omega n for the real part plus minus I times omega n 1 minus zeta squared under square root. And these real part and this imaginary part, we give them some names. The real part, we call it sigma, and the imaginary part, we call it omega d. So we can say the roots of the characteristic equation are negative sigma plus minus I times omega d. Okay? So if these are the roots of the characteristic polynomial, now what kind of response do I get in the free vibrations? If I move the system away from equilibrium and let it go, what kind of response do I get? I'm going to show you. But before that, I want to tell you that this omega d, which you see, it has also units of radians per second, because this portion has no units, so the unit of that is the same as omega n. That omega d, and which by the way is always less than omega n or equal to omega n, because this square root is less than 1 all the time. This kind of smaller frequency is what we call damped natural frequency. So omega n is natural frequency without damping, but if there is damping in the system, the frequency of vibrations is going to be omega d, not omega n. Why? Let's go and take a look. So here we have to now bring in the initial conditions, and we have to look at different kind of response that we get out of the system. So if we go back and look at the different scenarios based on these roots, scenario 1 is under this square root is positive. So 1 minus zeta squared is positive, so the roots are actually complex numbers. Well, under what condition 1 minus zeta squared is bigger than 0? When zeta is less than 1. When zeta is less than 1, then you will definitely have 2 complex roots, negative sigma plus minus I omega d. And you know, when you have complex roots with real parts, your solution is going to be what? It's going to be a harmonic portion due to this omega d, and this negative sigma is going to be a decaying exponential. So your solution is going to be a decaying exponential e to the negative sigma t, because negative sigma is the real part of your roots, times what? A to the sine omega dt plus b cosine omega dt. Okay, where a and b are determined from initial condition, the way I'm about to tell you. But look at this kind of response. What kind of response is that? This response is clearly a harmonic response. where the frequency of the oscillation is omega d, not omega n. That's why we call omega d damped natural frequency, the frequency of vibration when you have damping, and there is attenuation in the amplitude. If the amplitude is initially square root a squared plus b squared, over time it is going to go down. So the behavior that you would get out of the system is a damped harmonic. So you see here, this is a harmonic, and the frequency of this is omega d, but if you look at the amplitude, it shrinks over time. Ultimately, it gets to what? It gets to 0. Why? Because the energy of the system is constantly being dissipated by your damper. Your damper is converting it to heat or sound wave or both. So over time, your energy is dissipated. There is nothing externally to inject the energy back, like no external force or something. So ultimately, your system is going to stop moving. That's the same thing that happens to a pendulum with some damping at the joint. Okay, so you get a damped harmonic, and this kind of response in vibrations, we call it underdamped response, which means there is damping, but it's not strong enough to kill all the oscillations. There is still oscillation. Ultimately, the system will stop because zeta is less than 1. Zeta means what? Remember, zeta is c over 2 square root km. This guy is less than 1. By the way, in some textbook, they call this guy here, they call it C critical. So they say C is less than C critical. C critical is this number, square root 2 km. When your damping is less than damping critical, your response is underdamped. So if somebody says critical damping coefficient, C critical, that is this denominator, 2 square root km. Okay, I just want you to know that notation just in case. Now, what is A, what is B? Remember, A and B are unknowns. How do we find them? From initial condition. X at 0 is x naught, x dot at 0 is x dot naught. So plug in 0 in this solution, what would you get? Sine goes to 0, cosine goes to 1, and this exponential goes to 1. So all you will get is literally B. So B is x0. Then you need to take time derivative, plug 0, and set it to x dot 0. Now, when you take time derivative, what happens? The time derivative of this is what? Here, this guy has derivative. Also, this one has derivative. It's a product. So it's going to be derivative of exponential times the harmonic plus exponential times derivative of harmonic. So what's the derivative of that? Derivative of this is negative sigma exponential negative sigma t times a sine plus b cosine. This is for the first part. Now plus the exponential times what? The derivative of a sine omega d is a omega d cosine omega dt. Derivative of that is negative b omega d sine of that omega dt. That is your x dot. Now here, if you plug in 0, what would you get? Sines will be 0, cosines will be 1, and the exponentials will also be 1. So what would you get? You will get negative sigma times b plus what? A times omega d. This is equal to x dot 0. So now that you have x0, plug it here. That should give you a and b. So that is going to be your a, this is going to be your b, and this is going to be your solution, this guy here. That is your solution to arbitrary initial conditions x0 and x dot 0. You see there is a cosine and a sine, so there is a harmonic and there is an exponential. And if you want, you can write this a sine plus b cosine as sine of omega dt plus some extra phase, where phase comes from the arctangent command, and times some amplitude, where this amplitude again is these two guys squared. So this x is the square root of this one squared plus what? This one squared. And this phi is what? This is tangent inverse of basically this sine term over what? Over this cosine term. Okay? Yep. So you can write it that way. But clearly, again, you see it's a harmonic with damped amplitude. The amplitude is actually, if you look at the amplitude, your amplitude is this really. This is your amplitude. Although there is a constant x, but over time that x is multiplied by what? By an exponential term. So over time that amplitude, although in the beginning it's x, but next time it will not be x. This time it's going to be what? It's going to be x times what? E to the negative sigma. If at initial time is t0, here, how much have you moved forward? As much as a t. So it's going to be times t. Or if you want to write t in terms of omega d, it's going to be t e to the negative sigma. For t, you write it as 2 pi and then over omega d. Because in this system, the frequency of vibrations is determined by omega d, not by omega n. So the first amplitude is x. The next one is a decayed version of x. The next one, it's going to be 2 times that. The next one is going to be 3 times that, 4 times that, and ultimately it goes to 0. So this is the kind of response that you get if zeta is less than 1 and your system is under damped. Okay? Now, as I said, since the amplitudes are going down exponentially, there is a parameter that you define in this kind of response. We call it logarithmic decrement. What is that? You can show that if you divide the first amplitude x1 by the second amplitude x2, or the second amplitude by the third one x3, or the third one by the fourth one, and take natural log of them, the result of all of this is the same, and that is called the logarithmic decrement delta, which is a unitless entity. Now, how would you find it? Well, at any arbitrary time t1, which corresponds to one of these peaks, so let's say this is t1, you find the amplitude. So x1 is initial x times e to the negative sigma t1 times the sine function, because it's at time t1, and then you do it at the next peak, which is t1 plus td, and td is the period of the signal. So you plug that time both here, and you divide these two amplitudes and take a natural log. Okay? Now what happens? When you do that, these two x's would cancel. Since the sine function is a periodic function with frequency omega d, when you simplify this, well, what will you get? This is going to be sine of, if you do it, it is going to be omega d t1 plus what? Plus omega d td, right? And then plus phi. Well, what is omega d td? Based on what I know, if I multiply them together, the result is 2 pi. So this guy is 2 pi. And I know if I add 2 pi to anything, the sign of it will not change. So this is the same as sine of omega d t1 plus phi. And that is exactly this guy. So these two signs would cancel as well. This exponential can be written as e to the negative sigma t1 times e to the negative sigma td. And then this e to the sigma t1 and that one in the numerator will also cancel. And this negative exponential that is in denominator comes to the numerator, so it becomes positive exponential, and the natural log of exponential would cancel, so you simply get sigma td. And td is 2 pi over omega d, and omega d, based on what we just know, is omega n times what? Square root 1 minus zeta squared. So if you plug it in here, look. So for that omega d, I plug in basically, let's make sure. So sigma td, that's right. This sigma itself is zeta omega n, and omega d is omega n square root of 1 minus zeta squared. So those two omega n's would cancel because one is in the numerator, one is denominator. So you're going to get 2 pi times I and this guy in the denominator. So ultimately, this one here is going to be your logarithmic decrement. And if you look at your logarithmic decrement, the interesting thing is it's only a function of the damping factor. It has nothing to do with natural frequency. It's only a function of damping factor, or I can say really it's a function of damping coefficient mostly. Okay, so this logarithmic decrement, which shows the logarithm, natural logarithm of first amplitude to the second one to third one to fourth one, or n minus 1 to nth one, that depends on your damping factor. And this is the plot of it. So if you want to plot delta versus xi, so you want to plot this function, it is going to look like this. Now, interesting enough, for small damping factors, you can approximate this curve by a line. What line? The line of delta equal 2 pi zeta, basically just the numerator part of it. So you can approximate it only by the numerator part of it because zeta is very small, zeta squared is very small, so this guy can be approximated by 1 if and only if zeta is, let's say, less than 0.4 or something. So when zeta is less than 0.4, you can approximate linearly or delta with zeta, you say something like that. Now, if somebody gives you two amplitudes, x1 and x2, and say find zeta for me, you can do that. For instance, as just a numerical example, if I say this initial amplitude is like 0.8 and then this next amplitude is, let's say, what, 0.4, okay, let's just go by half. So in this case, delta is natural log of x1 over x2. So it's natural log of 0.8 over 0.4. So it's natural log 2. Yes? Now this is equal to 2 pi zeta over square root 1 minus zeta squared. Now here I don't know whether my zeta is below 0.4 or not, so I cannot just approximate it by the numerator. So I have to solve for this. And if I do so, I need to cross multiply both sides. You get this. And then what? Then what you need to do is to square both sides. If you do that, then you are going to get 1 minus zeta squared, the whole thing times natural log of 2 squared. This is equal to 4 pi squared zeta squared. And clearly this is a simple second order equation. You take this coefficient to the other side, and here you can solve for zeta. If I do it in MATLAB, let's see what number I can get. You are going to get 0.1097. You see, so if you want to go down by a factor of 2 each time, then you need something around 0.11 to do that. Okay, and natural log of 2, when I calculated it, the number is about 0.69 or 0.7. Okay, so you have to look at that number, and for that 0.69 or something, you can find some corresponding number. Now you see this is clearly a small number, so could I approximate it by this? because this guy is 0.69, and this 2 pi is clearly 3 times 1 4 times 2, so that is 6.28. And this one was about 0.11. And you see that if you multiply this by 6.28, you get somewhere around 0.69. So if I wanted to get this, I could simply divide delta by 2 pi and get xi. I can do the approximation here because my zeta was small, so I could just directly do it there instead of going through the second order basically algebraic equation. But that is the way that you can solve it for any general zeta, whether it's small or not. One extra thing I wanted to tell you before I move to the critically damped response is, you see here these two dash lines that are basically above and below your actual response. These two, they have a technical term. They are called envelope. So if you hear the word envelope, these are the envelopes of this curve, and they are positive and negative exponential e to the negative sigma times t, and your curve is always tangent to them. It is inside of these two curves, which are the envelopes of the curves. So your curve is between these two positive and negative exponential of negative sigma times t. Okay, scenario 2 is when you have a lot of damping in the system. That is called overdamped response. Your zeta is bigger than 1, or your C is bigger than C critical. And remember, C critical was this. So your zeta is bigger than 1. Well, another way you can write the roots of the characteristic equation is to write them this way without any complex I. That is when zeta is bigger than 1, or this guy is positive. So you're going to have two real roots where this negative number is going to be added or subtracted to this other negative number. And as long as both of those numbers are both negative, you're going to have basically two decaying exponential, one with the first root, one with the second root. You just need to make sure both of these numbers are what? Both of them are negative. And the answer is, are they or not? So let's take a look whether they are both negative or not. I mean, this one is definitely negative because both terms are negative, no doubt. And you know zeta is bigger than 1. What about this guy? Is this guy bigger than? Is this guy negative too? Well, the answer is yes. Why? Because zeta squared minus 1 is less than zeta squared. So if you take a square root, you can say that the square root of zeta squared minus 1 is less than zeta. And if you bring this to the other side, you can see that negative zeta plus that the square root of zeta squared minus 1 should be negative, and that is exactly this guy. So in this case, both of the roots are negative real, and so you get two negative exponentials, two decaying exponentials. Now, if you plug in the two initial conditions, x0 and x dot 0, you can solve for a and b. In this case, a and b are going to be quite big in this formula, and if you plug them back, as I said, you're going to get two decaying exponentials. So your actual response is going to start from x0 with initial slope of x dot 0, right? That's your slope. And it is going to exponentially go to 0. And the two envelopes, again, of your curve are these two responses. This one and this one. These are your envelopes, right? So your actual curve is going to fall between these two. And this is how your system will respond. It directly goes to 0, and you are not going to see any oscillation in this case. So no oscillation, pure exponential decay. That's called overdamped response. Okay. Finally, we have critically damped response. That is when zeta is 1, or C equals C critical. In this case, again, no oscillation, but in this case, both of the roots are simply equal to negative omega n. Really? Yes, because if I go back and look at this previous one, you can see what happens when zeta is 1. When zeta is 1, this whole term goes to 0. This is 1, so your both roots are equal to each other, or you have repeated roots at negative omega n. So you're going to have two decaying exponentials with power negative omega n. One term is a times that, one term is bt times that. That's because of the repeated root. And so if you apply two initial conditions, you can find the constants a and b, and this is going to be your final response. Now, because not only you have a exponential, you have a t times exponential, and t times exponential helps the whole thing goes to basically 0 faster. So in this case, these are different scenarios that you can have. They all start from x0 based on different x dot zeros, whether it's positive, negative, or 0, different initial slopes. All of them exponentially will go to 0. You see, if it's negative, it can have one basically undershoot, then goes to 0. But if it's 0 or positive, guess what? There will be no undershoot. They are directly going to 0. The same goes if x0 is negative. So if your x0 is negative, again, depending on whether your x dot 0 is bigger than 0, less than 0, or equal 0, again, you have different responses. So if it's equal to 0, you're going to get this kind of response. If it's negative, you're going to get this. And if it's positive, you're going to get this. So you're going to get one overshoot. You pass that number 0, and then you go to 0. Okay, so the fact that you never pass value of 0, no undershoot, no overshoot, depends on whether the sign of x0 and x dot 0 are opposite of each other or the same sign. If they have the same sign, no overshoot, no undershoot. If they are different, you might get one crossing of 0 before it exponentially goes to 0. But in general, this is typically the fastest kind of exponential decay that you can get. And in robotic systems, when they want to control joints, they typically pick their PID controller gains, so the response of each joint is a critically damped response rather than overdamped response. And in robotics, we never really want underdamped response. We don't want our arm to basically to reach a position, and when it reached the position, it basically does a couple of oscillations around it before settling down at that joint angle, right? You want it to start from initial position to directly go there and stop. No overshoot, no undershoot. You really want a critically damp or overdamp response, and because critically damp is a little bit going to 0 faster, we typically pick critically damp response in most of PD tuning or PID tuning for robot controls. So just keep that in mind. Now let's look at one example, and then I want to talk about state space diagrams for both this system and the previous video where I talked about the ones without damping. We're going to see the difference between their state space plots. But let's first look at one example together. So here we have this basically pendulum that is starting originally horizontally, and there is a spring and damper somewhere along the way attached to it at distance a. The mass is concentrated at distance L. You want to find the damped natural frequency of the system if the angle here is theta, and this theta is first of all measured from static equilibrium, and it's a small angle. So you see you're making two assumptions. Theta is measured from static equilibrium and it's small. What does the static equilibrium mean? Well, because this mass is here and it applies mg, which applies a torque about O, the system wants to go down clockwise. But as soon as it starts going clockwise, this damper and this spring starts forcing start applying forces to the system to bring it back, right? This guy applies some k times some force, this guy applies c times some velocity force. But ultimately, it stops at some theta statics at which the moment of these two forces about O is equal to the moment of this mg about O. Okay, so basically you can say that mg times L at that position is equal to k times a, assuming that that angle is small, the displacement of this point down here is going to be a times theta, again assuming that theta is small, so it is going to be k a theta, that's the force, times a, that's the distance, then plus c times the velocity of that point is going to be a theta dot times a. Okay, and this is theta static. Now when it's in a static scenario, the damper will show no force because it's a constant theta. There will be no theta dot. So you can from here find the angle at which the system comes to equilibrium, static equilibrium, and then the theta that we have here is measured from there. So initially you go down a little bit, and then my actual theta is measured from this point. And this is a horizontal line. Okay, so this is how we measure theta, and again we assume that theta and the theta static, they are all small, so that the spring is way more, it's a big, strong spring for that kind of mass. Okay, so your angles are going to stay small. Okay, so now going back, we have to draw the FBD, of course, of this system. So if we draw the FBD, as I said, the force here is mg. There are two pin forces here. And there is a spring force and there is a damper force. The spring force, as you remember, is Ka theta, and this guy is Ca theta dot. And this is A, that whole distance is L. But remember, we said that everything is measured from static equilibrium, therefore we neglect mg because it will already be cancelled by this extra deflection of the spring. So that is all you have in the FBD. You don't need to consider mg. Now, if you take total moment about this point, these two forces will be multiplied by n, and they are both creating counterclockwise moment while your angle is clockwise, so they both create a negative moment, as you can see. Seems like there is one typo here that I need to clean up. And this one is A, not A theta. And this is equal to the polar moment about point O times theta double dot. And in this case, since it's just a mass point at distance L, it's going to be ml squared. And from here, if you bring everything to one side, this is going to be your governing equation of motion. If you look at it, this is very similar to the mass spring damper system, right? So you have C over m theta dot K over m theta. The only thing is you have these two unitless ratios multiplied by that. A over L square for both of them. Therefore, you can predict your natural frequency to be square root K over m times AL. And your zeta is to be A over L C over 2 square root Km. And your natural damp frequency, omega d, which is omega n times square root 1 minus zeta squared, is to be this guy, if you simplify it. So here is how to find the natural frequency of the system. And this is assuming that the system will oscillate. So here I'm assuming that this xi is what? Less than 1. Otherwise, natural frequency has no meaning, right? Because the system will not oscillate, you will not see any frequency. So this has only a meaning if and only if this assumption is valid. You have to pick those numbers so that zeta is less than 1. Otherwise, it is not going to oscillate. It will be critically or over-damped response. So hopefully this example is helping you. Now, as I said, I want to talk about the state space diagrams. So since these systems are all single DOF, you basically have the function and its time derivative, and you can make a simple 2D state space. So for instance, in the mass spring system, what you can do is to plot x dot versus x, or in this pendulum, you can plot theta dot versus theta. Okay, these are the states of the system, and you want to see what kind of response you would get, right? So you start from x0 and x dot 0, so you start somewhere here. And as time goes on, what kind of trajectory would your system go through? So we call it the state space trajectory, right? We want to see what kind of response you would get. If the system is underdamped, overdamped, or critically damped, or if the system has no damping altogether, then what? If the system has no damping altogether, right? It's an undamped system like the previous lecture that I had. What kind of state space will I get, right? So first, let's look at the scenario that there is no damping. If there is no damping, going back to the previous lecture that I talked with you, look, the solution was a simple sine function or a simple cosine function. Remember? Look here. Your theta or your x is simply some magnitude times sine of some omega nt plus some phi. That's all it is, right? The same goes for x. So if I go back here, and for a second look at it, so let's look at the mass spring system with no damper, right? Your x is capital X times sine of omega dt plus phi in general. Take a time derivative. X dot is going to be what? It's going to be x omega d cosine of omega dt plus phi. Now, if you want to eliminate time between x and x dot, what would you do? Well, all you need to do is to square them. If you square them, then the bottom one, you divide both sides by x squared omega d squared, and the top one just divide by capital X squared, and then add them together. What would you get? You get the small x of t over capital X, the whole thing squared, plus the x dot of t over capital X omega d, or omega n in this case, really, because there is no damping, so I have to replace that by omega n. This is equal to sine squared plus cosine squared, which is what? Which is 1. Now, if these two are my axes, what kind of equation is that? Well, clearly that's an ellipse, where your semi-minor and semi-major axes are the amplitude of x and the amplitude of x times the frequency, right? So in this case, if I want to plot it for myself, right, then I have to plot an ellipse where I have a capital X, and capital X is the amplitude, which in this case it comes from these two numbers squared, and then x times omega n. So let's say this omega n for a moment is less than 1. Okay, so along the x-axis you have a bigger axis than along the y-axis. If that's the case, the kind of curve that you will get is going to be something like this. where this distance from here to here is amplitude x, and this one from here to here is x times omega n. So you would get what? You would get an ellipse. And your initial point is somewhere on the ellipse. As time goes on, let's say first x gets bigger, so you go to the very end of the amplitude, then you start coming back. So first you go to big x's and x dot of 0, so and then so you're going this way, and then you start coming back. So the way that you move on this trajectory is this clockwise manner. Okay, so your trajectory is going to be an ellipse with a clockwise manner in this case. Or depending on the direction of x dot, it could be counterclockwise. But regardless, you're going to move on a closed curve. And what does a closed curve mean? Closed curve means that the energy of the system is conserved. It is not going to change. Nothing is going to waste the energy of the system in this case. There is no damping. So if you see the state-space trajectory is a closed curve, that means the energy of the system is not being wasted. Your system is closed curve. Now, how do you know the area inside this curve is energy? Where would you get that? Well, let's take a look. What am I integrating here? I'm integrating the integral of x dot versus x, correct? When I plot x dot versus x, this is any curve, and I'm looking at the area under the curve. This is the kind of thing that I'm integrating, yes? Now, what kind of entity is this? Integral of v dx, right? So what is that here? So if you want, we can do something interesting here. So I multiply by a dt and I divide by a dt, right? You don't mind if I do that. Now, what is this? That's also x dot, right? So I get integral of x dot squared dt. Now, in this case, remember your x dot is actually this one. This is your x dot. So if I go and plug it in, and I have to do it over one period, because over one period you go over one curve and come back to the start and repeat. So I integrate this from 0 to t. So it's going to be 0 to t of what? Magnitude squared of oscillation x squared times omega n squared, right? And then cosine squared of omega n t plus phi dt. That is the kind of thing that I'm integrating. Now, clearly, these two have nothing to do with the time, so I can get them out. And for cosine squared, I use 1 plus cosine of 2 times that entity divided by 2. So whatever this one is. And if I integrate 1/2 versus time, I'm going to get t over 2. And the integral of cosine of 2x is going to be 1/2 sine of 2x, with another 1/2 is 1/4. And if I calculate it at 0 and t, just check my previous videos, I can show that this part of the integral will go to 0. Okay, so this is going to be it. That's it. So now look at that. It is going to be x squared omega n squared t over 2. Right? So this is the thing that is actually inside that curve. So first of all, let's see what kind of entity is that, and second, that one actually is an interesting formula, because first of all, the area under that is proportional to the time that it takes to go around to the omega n squared and to x squared. But remember that omega n and t are related. T is 2 pi over omega n. So if I want, I can get rid of one of the omega n's, and then that 2 and this 2 would cancel. So if you simplify this a little bit, you are going to get x squared, and then pi, and then omega n, correct? That's it. So now look at it. Okay, you see that is proportional to omega n, and it's proportional to the amplitude of the oscillation squared. Now, this guy has units of 1 over second, because radian has no units, and this guy, let's say if it's the spring damper mass system, this has units of like meters squared. So this is the kind of entity that you get, meter squared over second. And what kind of entity is this? Well, so to answer that, we look at energy. Unit of energy and work is both joules, and joules is Newton meter, and Newton is force is kilogram, meter is F equal ma. So this guy is meters per second squared, A times kilogram. So it is going to be meter squared kilogram over second squared, right? That's the unit of energy. Now, if I divide the energy of the object by the mass of the object, then this kilogram part goes away. And if I integrate this versus time, I'm multiplying it by the unit of seconds. So 1 power of that goes, and I get this. So what I'm doing here is I'm integrating energy versus time and dividing it by the mass of the object. So you see, if the energy of the system over time does not change, okay, if the energy of the system is a constant, over time does not change, right? Then the area of this curve, the area enclosed by the curve, should also not change. And therefore, the curve should stay a closed curve, so the area enclosed by it, inside of it, does not change. So you see why it is related to the energy, and if there is no damping, there should be a closed curve system. Now, on the other hand, if there is a damping in the system, the behavior is going to be different. You still start at this initial point, but over time, the energy of the system is going to go down. So what kind of state space trajectory will you get? Well, in this case, it's not going to go on an ellipse anymore. So if you start here, again, this is x dot and this is x. If you start at this initial condition, you start here, and then as you move on, remember your amplitude is always multiplied by a negative exponential, assuming that the system has an underdamped response for now. So assuming that zeta is less than 1. So you start going through the ellipse, but the total radial distance, which is the amplitude, it is going to go down over time. So what kind of curve would you get? If it's clockwise, let's say, you are going to get this. Your radial distance is going to go down, and you're going to go to a spiral until your system will settle down at 0 and you lose all of your energy. So the area enclosed by the curve goes to 0 over time. Yes? That is the kind of response that you get when the system is underdamped. Now, if so overdamped or critically damped, you are not even going to go through these cycles. You directly go to 0. Now, to simulate that for you here, I made a simple mass spring damper system, and I send out x and v to the workspace, x versus time, v just directly, and I have all the initial conditions here, x0 and x.0, and I can pass to it the values of K, C, and M, right? And of course, this is the equation of motion here. Actually, this is x double dot, not that one. So this one is x double dot. This is basically, in this case, this one here is sum of fx. Okay, so that is sum fx. And divided by mass to get the acceleration, double integrated to get position and velocity. So here in this script, I pass the numbers and I want to see different scenarios. So first, I have no damping with K of 100, M of 1, initial condition all non-zero, final simulation time 10 seconds. I simulated and then plot for you x versus time and then x versus x dot. So you see what kind of response you would get. And you should definitely get the closed ellipse and the sustained oscillation, which I mentioned in my previous video. There we go, look. So you see it is an ellipse, right? And in this case, look, along the x dot axis, you're from negative 10 to 10. Along the x-axis, you're almost negative 1 to 1. What does this tell you? When your y or x dot axis is bigger, that means your omega n is bigger. And it is. In this case, your omega n is 10. Because square root k over m, square root of 100 over 1 is 10. And that's exactly what it is. Look, your semi-minor axis is 1. Your semi-major axis is 10. So you see the ratio between these axes, in this case, this one, right? And then this one, the ratio between these is 10 to 1, which is exactly your omega n of the system. And your oscillation is sustained oscillation. There is no damping whatsoever. So this is the state space response when you get when there is no damping. Now, on the other hand, if I add a little bit damping, still make sure zeta is less than 1. How do I make sure? I have to make sure c over square root 2km is less than 1. Now, what is the c critical in this system? The c critical in this system is how much? Square root km times 2. So this guy is square root 100. That's 10. That's 20. So as long as my C is below 20 in this system, I'm under damp. So anything below 20 would work. So let's go with 10. Okay, that should put my zeta at 0.5, and I should get a nice under damp response. So let's get the under damp response. There we go. Clearly, you can see that the system starts from this, and then there is a little bit of oscillation here, a couple of, and then very fast goes to 0. And you see here, you're starting from there, and then you have this spiral, and ultimately you settle down at 0, 0. Now, zeta is too big for this system to see a good spiral and a bunch of overshoot, undershoot. So I'm going to bring the C down to maybe 2 and make it quite a bit smaller. So I make it like 0.1. There we go. Now you see it a lot better. See, now you clearly see the under damp response better, and you see the spiral a lot better. Correct? There we go. So this is under damp response state space trajectory. Now, on the other hand, if I make C to pass 20, like 30, I should definitely get over damp response. So let's do it. There we go. Look, your response exponentially goes to 0 very fast, and you start here, and without doing any spiral around 0, you directly go to 0, and that's it. So if you go back to this diagram here, let's see where I did that. Right, in this case, you basically start here, and then boom, you go to 0. That's a over damp response. Critically damp is very similar. So if I make C to be 20, so zeta is exactly 1, look, that should produce a very similar response. There we go. Okay, and if you want, we can generate all of them side by side. All we need to do is to apply 3 different C's, run this data, do a hold on, and then what? Plot them all versus each other. Let me actually do that so you can see that one as well. Okay, here I have modified the code. There we go. You can see that. And you can see for zeta of 0, it's a closed curve. For zeta of 0.1, it's a spiral. For zeta of 1 and 2, they are these critically and overdamped responses. And you can see the appropriate response here on the right side. So on the right side, so x versus t, x dot versus x, and this is the code that I have modified. I just created the labels. I used the Greek letter zeta. I use different colors, and everything is the same. If you want, I can share these two for you under the video description so you can play with them and learn from them. So hopefully the video was useful to you. I'll see you in the next lecture. Thank you.